If you hold a penny at arm's length, the penny blocks out the full moon, and you might think, looks larger than the moon, at least from your perspective. The reason is that the penny, being so close, forms a larger image on the retina of the eye than does the more distant moon. The brain interprets the larger image of the penny as arising from a larger object. The size of the image on the retina determines how large an object appears to be. However, the size of the image on the retina is difficult to measure. Alternatively, the angle theta subtended by the image can be used as an indication of the image size. Here we show this angular alternative, which has the advantage that theta is also the angle subtended by the object and hence can be measured more easily. The angle theta is called the angular size of both the image and the object. The larger the angular size, the larger the image on the retina, and the larger the object appears to be. The angle theta, measured in radians, is the length of the circular arc that is subtended by the angle divided by the radius of the arc, as shown here. Within the same geometry, we can illustrate the situation for an object of height HO, viewed at a distance DO from the eye. When theta is small, HO is approximately equal to the arc length, and DO is nearly equal to the radius, so that theta in radians equals HO divided by DO. An optical instrument, such as a magnifying glass or a telescope, allows us to view small or distant objects because it produces a larger image on the retina than would be possible otherwise. In other words, an optical instrument magnifies the angular size of the object. The angular magnification, or magnifying power, m, is the angular size, theta prime, of the final image produced by the instrument divided by a reference angular size, theta. The reference angular size is the angular size of the object when seen without the instrument. A magnifying glass is the simplest device that provides angular magnification m equal to theta prime divided by theta. In this case, the reference angular size, theta, is chosen to be the angular size of the object when placed at the near point of the eye and seen without the magnifying glass. Since an object cannot be brought closer than the near point and still produce a sharp image on the retina, theta represents the largest angular size obtainable without the magnifying glass. As shown here, the reference angular size, theta, is approximately equal to HO divided by n, where n is the distance from the eye to the near point. To compute theta prime, we assume that the object is a single converging lens, with the object located between the focal point of the lens and the lens. The lens thus produces a virtual image that is enlarged and upright with respect to the object. Assuming that the eye is next to the magnifying glass, the angular size seen by the eye is theta prime approximately equal to HO divided by DO, where DO is the object distance. The angular magnification is then given by m equals theta prime divided by theta, which is approximately equal to HO divided by DO divided by HO divided by n, which equals n divided by DO. According to the thin lens equation, DO is related to the image distance DI in the focal length f of the lens by 1 divided by DO equals 1 divided by f minus 1 divided by DI. Substituting this relation for 1 divided by DO into the expression for m leads to m equals theta prime divided by theta, which is approximately equal to 1 divided by f minus 1 divided by DI times n, which is the angular magnification of a magnifying glass. Two special cases of this result are of interest, depending on whether the image is located as close to the eye as possible or as far away as possible. To be seen clearly, the closest the image can be relative to the eye is at the near point, or DI is equal to negative n. The minus sign indicates that the image lies to the left of the lens and is virtual. In this event, m is approximately equal to n divided by f plus 1. The farthest the image can be from the eye is at infinity, or DI equals negative infinity. This occurs when the object is placed at the focal point of the lens. When the image is at infinity, the magnification equation simplifies to m is approximately equal to n divided by f. Clearly, the angular magnification is greater when the image is at the near point of the eye rather than at infinity. In either case, however, the greatest magnification is achieved by using a magnifying glass with the shortest possible focal length, since the focal length f is in the denominator.